This chart tracks managed honeybee populations in the United States since 2010. For over a decade, the line holds relatively steady, with beekeepers weathering historical winter losses of around 30%. But between April 2024 and April 2025, the data plummets. In a single year, the industry lost 55.6% of all managed colonies. The catalyst for this drop is a microscopic parasite called the Varroa destructor mite. To understand what the honeybee experiences, imagine a tick the size of a dinner plate latching onto your back. Commercial beekeepers managed these mites with relative success for decades. They relied on a chemical miticide called amitraz, which effectively suppressed the parasite and kept winter colony losses to a manageable 15 to 20%. That baseline shifted in late 2024, when standard treatment protocols suddenly failed. Beekeepers who executed every preventative measure flawlessly opened their commercial hives to find catastrophic collapse rates between 70 and 100%. When a primary chemical defense fails at this scale, it signals a breakdown in the biological infrastructure that secures the American food supply. USDA investigators sampled mites from collapsed colonies, finding virtually all possessed genetic resistance to amitraz. The industry's primary defense was useless. We previously assumed these parasites drank hemolymph. We now know they dissolve and consume the bees' fat bodies, critical for energy and immune defense. As the mites drain those vital fat reserves, they act like microscopic dirty needles. With every puncture, they inject pathogens like the deformed wing virus into the bees' weakened system. A chemical-resistant parasite that drains immune reserves and injects lethal viruses creates an unwinnable biological war. Inside the hive, colony collapse accelerates faster than the queen can produce new workers. Explaining a loss this massive requires a look at the wider agricultural environment and the biological concept of synergy. Synergy occurs when the presence of one ecological stressor amplifies the lethality of the others. The first multiplier is pesticide exposure. University research shows that neonicotinoids, a widely used class of insecticides, disrupt the gut microbiome of bee larvae, impairing their immune systems at the earliest developmental stage. A healthy colony might survive a mite infestation or tolerate a sublethal dose of agricultural pesticides. But the combination of a pesticide-compromised immune system and a virus-injecting mite creates a rapid, lethal synergistic reaction. Climate disruption acts as a second multiplier. Unseasonably warm winters eliminate the natural brood break when queens stop laying eggs and mite reproduction pauses. Live out of freeze, the parasites breed year-round. Finally, monoculture farming creates a nutrition gap. Miles of identical crops provide a massive but brief window of food, followed by months of total starvation. This death spiral is a mathematical inevitability. It happens when an invincible parasite meets a bee population already poisoned, starving, and climate-stressed. Because commercial pollination is an $18 billion industry, this biological collapse hits the consumer directly. As growers struggle to rent enough hives, agricultural economists project 5 to 10% price increases on dependent produce like blueberries, cherries, and almonds. To stop the losses, researchers are moving past crude chemical miticides and into the realm of precision genetic engineering. This animated diagram illustrates RNA interference, or RNAi. This technology functions as a targeted biopesticide. By selectively silencing the exact gene the Varroa mite uses to reproduce, scientists can halt the parasite's life cycle without harming the bee's DNA. Simultaneously, specialized breeding programs are developing mite-resistant honeybee genetics. Beekeepers track specific lineages, like this blue-marked queen, to cultivate hygienic colonies that naturally remove the parasites. The parasite has currently outsmarted our chemicals, but precision science is escalating the evolutionary arms race into the genetic code to secure the future of food. These genetic and biological solutions will take years to reach commercial scale. In the meantime, the honeybee population requires immediate stopgap measures from the public to survive. The first step is addressing the chemical multipliers. Eliminating neonicotinoid pesticides in residential gardens removes the sublethal doses that compromise bee immunity. The second step is planting diverse native flowers that bloom across multiple seasons. This provides continuous nutrition necessary to counteract the starvation cycles of industrial monocrops. Finally, purchasing raw honey from local beekeepers provides the immediate capital these operations need to replace the 55% of colonies lost this year. While global agriculture seeks a structural cure, these localized actions act as a vital buffer. They provide the chemical-free zones and diverse nutrients honeybees need to survive until the next generation of genetic defenses reaches the field.